All right, so yeah, it's all about particles in the air or particles in a gas colliding. So if you put gas into a smaller area, will there be more collisions?
Yeah.
Yeah. And if you let gas into a big area like this room, will there be less collisions?
Yeah.
Yes, so just remember that. It's all about collisions when we're talking about gas pressure. So we left off yesterday with those three graphs. So I'm just going to sketch those up here again really quick. 1, 2, and 3. We didn't actually finish this. This one was volume and pressure, right? This one was temperature and volume. And this is temperature and pressure. Okay. Now, before I have you guys tell me which one's which, what is this at constant what? Constant temperature. Why is temperature held constant? Why on this graph do we have to hold temperature constant? Remember, all three of them, PTV, play a role with each other. So why do we have to hold temperature constant on the pressure volume graph?
Because if it wasn't, then one would be more than the other, right?
If it wasn't held constant, sort of, if it wasn't held constant and we actually did an experiment in lab, which we will be doing, to see how volume and pressure interact, if we didn't hold temperature constant, then we would really never know what? The what? The relationship between just volume and pressure, right, good. In other words, let's say the temperature was hot for one experiment and then it was cold for another. The volume and pressure relationship might change and you might not know, okay, was the volume change the reason or was it the temperature change? Really, we just want to focus on two of the variables. So for all three graphs, you got to hold one variable constant. In lab, you're doing this one and this one. Okay, I got a demo today to show you this one. All right, actually the demo applies to all, but the one on the right is kind of more appropriate. So we're always holding one constant. So at constant pressure, and this one is at constant volume. Okay, before I forget, I got this thing from Hudson Valley. Let's see. Any of you interested in engineering? There is a, it's called We Are Hosting Experiencing Engineering, an evening of panel presentations and discussions on Wednesday, November 4th from 6:15 to 8:30 p.m. at Hudson Valley Community College's Bulmer Telecommunications Center. The panel will consist of college students and working professionals who will discuss engineering study and careers. During this evening, you will learn about different engineering careers, college experiences that are common to a 2- and 4-year school offering engineering programs, and scholarship opportunities. So if you want one, I got a bunch of these. If you want one of these pieces of paper, just come and get it after class. If you're interested in engineering, you might want to go. So that's that. All right, back to this. Who wants to come draw one of these lines? Hey, sir. Who wants to show their knowledge?
I want to do it.
All right, pick one.
I'll do volume and temperature at constant pressure.
Come on up.
One. You want to toss it?
You just grab it. All right.
This one, right?
I guess whatever one you said you wanted to do. Okay, pick someone to do another.
Oh, that's not up to me.
You don't want to do it? Does anyone else want to volunteer? Come up and draw a line.
I'll draw a line.
Nope, you're good. Come on up, Nicole. Are you going to pick someone or do you want me to pick somebody? Do you want me to pick somebody? All right. Who's it going to be? Evan. Okay, Evan, you got the last one. So these may or may not be correct. We'll talk about it.
Zach's is incorrect.
So, let's think about it using our paper. Remember, we stuck the pen or pencil through the one we hold constant. So temperature is constant. If I turn the paper either this way or this way, what do we notice about pressure and volume? They do the same thing or they do opposites? They're opposites. One goes up, one goes down. One goes up, one goes down. What's that called? What type of relationship is that called? Indirect or inverse. So that is correct. That is correct. Very good. As one goes up, the other goes down, so the line looks like that. High pressure gives me a low volume. Low pressure, right? Low pressure. I might have said that backwards, sorry. Low pressure gives me a high volume. High pressure, low volume, right? So just look at the two scales. Where does that line meet X and Y? It's high on the Y, low on the X. Low on the Y, high on the X, so that's indirect. Those are indirectly related. One's high, the other one's low. Temperature and volume, and temperature and pressure. These are both, well, direct relationships. Good. See if it makes sense. If I do this one, constant pressure, put the pen in the P there, and the pressure. If I increase the temperature, volume goes up with it. If I decrease temperature, volume goes with it. So no matter what I do with temperature and volume, they do the same thing. They both go up, they both go down, that's direct. Constant volume, it's the same thing. If temperature goes up, pressure goes up. If temperature goes down, pressure goes down. Direct relationship. Okay? Justin, is that Pepsi can, is that boiling yet? Can you turn it up to like 8? Nice. Okay, so what does this mean? A low temp, low pressure. High temp, high pressure. Low temp, low volume. High temp, high volume. All right, this one, breathing, is what I talked about, I think yesterday or the other day. Yesterday. If you inhale, you're compressing the air into your lungs, right? Lungs are small, the room is big. So when you breathe air in, you have high pressure because the volume of your lungs are small. If you exhale, the air is filling up this room. The room is really big, so that's going to have low pressure. The air pressure outside your body is lower than the air pressure inside your lungs because it's confined. Gas is confined. It's going to bounce around, more collisions, right? So that's going to be a high pressure with low volume. Here, temperature and volume. Hot air balloon. How's that work? How do hot air balloons work?
The hot air. And they fill up the balloon. And then it goes up.
Hot air. Fill the balloon. It goes up. Okay, let's explain why. They pull the thing. It goes, right? Flame comes out.
It's
Use this graph to explain.
so like the temperature goes up, so
So what happens to the air in the balloon?
it like goes faster.
Expands.
It expands, takes up more space. So the particles are this close together. Then we heat it up, the particles spread out. Now they're this close together. They spread out. Why does that allow the balloon to rise? Don't say hot air rises. That doesn't explain why it rises. It just says, it's just stating it rises.
Because the wind, the updraft takes it up, right?
Nope.
Updraft. Okay. The updraft.
Good try, Ryan.
Updraft destroys buildings, you know.
Some of that could be involved, but
Updraft. It's when the wind. Okay, so.
hold it. That's not what we're doing right now. So stop it. Hold on.
I'll
So-
do a demonstration.
Why does something float in water? Less dense. So why does a hot air balloon float in air?
No, I got it. The hot air is less dense than the air.
Right. Hot air. So the air in front of my face right now has a certain density. The particles have a certain space between them. If I was to heat the air up in front of me with a flame, that air, we couldn't see it, but that air would start to rise. Why? Because the particles spread out and become less dense than the air around it. Just like that thing over there. I told you the thermometer yesterday, the little spheres rise and fall based on density. Air works the same. You can float in air, just like you float in water. No one really describes it that way, but it's the same concept. So a hot air balloon is just floating because it's less dense, but you need that heat. So if you don't pull the cord and the flame doesn't come out, what happens to the balloon? You don't heat up the air in a hot air balloon, what does the balloon do? It comes back to the earth because the density goes back to normal. The air comes back closer together. At my in-laws, there's a hot air balloon near their house. So in the summer, they have a pool. We go there, hang out in the pool, and like all these hot air balloons go over. And sometimes they get real low, and then all I hear is like they keep frantically pulling to try and not crash into the trees. I don't know if it's like people training on these things or what. There's always a lot of them. But I always think of this. I know that sounds crazy, but
I want to fly a hot air balloon.
yeah, it sounds cool.
And then how
it
do
looks
you?
cool.
If you want to go high, you drop the bags there. You just start throwing like bags.
You get
down.
rid of weight, but you also hold
How
the
do
thing.
they get the flame?
There's fuel. There's fuel in there.
There's fuel on it?
Yeah, it's like
What
big
is that
engine.
for?
Our sluice is like
There's a
jacked.
tank.
Oh, the window.
But,
The wind hit.
You mean
The
like the
wind
exhaust?
that happens is
Yeah.
it comes down hard
Where
and it
else?
hits the
It's
ground.
probably like a
So
burner.
it pushes
So
back
it
up
just
and it can take off.
kind of just burns with it. You know what I
It's
mean?
just like breathing inside.
If it's really
Well,
windy.
a little bit.
Because we're like in the Midwest. Though.
It's above their
Yeah,
head.
like if it's
so
really
like they have
windy,
to pull that.
or like you have a
whatever.
trail, like you.
All right, so back to this. Stay with me. Stay with me. Focus. So, hot air balloon is a good explanation here. Increased temp, increased volume, it's expanding, right? Air is expanding. That's why this makes sense. And then temperature and pressure, you take any sealed container that has air in it and throw it on a fire, what's going to happen to it? It's going to blow up because of the pressure, not because of the flammability. If I took this container, okay, and I sealed it, okay, put the top on it. Let's say it didn't melt. Okay, let's say it doesn't melt. I threw this on a bonfire, it would explode. Not because water's not flammable, but the pressure would build and this probably the top would pop off, right? So the weakest spot would explode. It's because of all the pressure building. When you heat it up, what do particles do? When you heat things up, what do? They move faster, more kinetic energy. If they're moving faster, more energy, do they hit each other more often? Yes.
Yep.
More collisions, more pressure. Okay? Let me go check on that can. Hold on. I'm gonna need some help.
Well, you know what? Corey, how bucks for that draft game question? It's not every 5 seconds.
I'll help you if needed.
Did you hear how like people from FanDuel like go on DraftKings and win like a bunch of money because they know all the stats and everything? And people from
Alright, you guys can come back, grab glasses.
FanDuel and they do the same thing. But they make so much money, they make like triple what they make at the place.
Really?
Yeah.
Because it's like that.
Grab your glasses. Go back to the Pepsi can.
Oh, no, that's not screen print. All I do is curl, yo. That's not screen print, right?
Get your glasses.
Yeah, sure, no problem.
Yes, sir. Just in time.
Screen print.
Chemistry magic.
Actually, that is screen. No, it's not. Except for this like this time. This is also.
You guys gotta be over here so you can see this. So come over here. Come over here. Okay. Either you're gonna be in that one. Xavier. You're gonna be in that one. You may or may not need it. Okay. I need someone to help me. Okay, alright, hold on. Let me show you what you're gonna do. Let me show you what to do. Evan's gonna do it. So you're going to hold it here. When I say go, you're going to flip it upside down. Like, then take this, put the whole can upside down. Okay? So I'm gonna record it. So hold on. Alright, you guys ready? Throw your glasses on. Ready? Hold on.
That was very encyclopedic.
Okay, go write down why that happened. That's it. It's over. That was awesome. That's a really good one. That was really good. Don't say anything. I want you to write in your notes why that happened.
Is there actually Coca-Cola in there?
Well, Pepsi. So it's never Coca-Cola. Go write down why that happened in your
Alright, go
notes.
back up.
I don't know why. You know why that happened?
Well, you see. Hold on.
Bro, I didn't know I was gonna do that.
My kneecaps were freezing.
Alright, let me give you a little bit more explanation. Inside the Pepsi can was there was no Pepsi, it was just a little bit of boiling water. So on the hot plate, the water was boiling. You need to know this, okay? Then, Devin grabbed it, flipped it upside down into the cold ice water. I assume you saw there was ice in that. Then you saw what happened. Explain why. It does have something to do with this stuff, okay? So I'll give you a few minutes here on your own. Think about it first. Write down some things. What?
We get to talk to each other about it?
Yep. Then you're gonna come together and talk about it, and then you're gonna tell the class what you decided. So go ahead. Don't discuss right now. This is all on your own first. What happened using these are called gas laws, right? So use these gas laws. We got to name them. I forgot to give you names. But go ahead, think about that. Boiling water flipped upside down in cold water, and then you saw what happened. And Sarah, make sure you get these down, okay? Oh, I love that. You with the teacher, I assume? Okay. Just, you're on your own right now. You're going to be talking here in like 2 minutes. All right.
I think I'm wrong.
Spitball.
Spitball, that's fine. So great things. Again, spitballs.
I have 2 ideas. I think the one I originally thought was right.
I got another demo for you tomorrow. It's going to be very similar. Also pretty good. I like these pressure demos.
I didn't expect.
You do with the glasses, huh?
We should
do it with the glass next time.
Alright, so do we have an odd number? We do have an odd number, don't we? That's okay. Okay, Jenny, you're going to have to talk to me still. Alright, you guys push your desk together over there. You guys push your desk together. Move the desk. Move the desk. Let's go. Yes, move the desk. Physically move the desk. Let's go. Move on. You got 2 minutes.
The pressure didn't stay constant.
Talk to each other.
As it explodes, you turn it super quick, and it gets small, and it starts exploding everywhere. Mr. McCoy, can we do a pressure demo? I got an idea for it.
Hold on, let's. After we explain this, then you can tell me.
No, but it's. I just want to say that. So we get the we did like same exact setup we did like boiling water, boiling water, right? And ice water, and we get a piece of pure potassium, and we put it in the water, and as soon as we put it in the water, we flip it in the thing so it gets smaller, and then it explodes.
Would it work though? Would one reaction happen before the other? Like if you
It's not a chemical reaction.
But wouldn't the potassium, like, once it touches the water,
I don't know.
I'm pretty sure it would. Isn't that right, Mr. McCoy?
We should experiment.
I think he's not listening. Once the
Yeah,
potassium
it
touches
would.
water,
I'm not. That's not good. Yeah, you would be containing. You wouldn't even have to flip it. If you put it in a soda can, it could blow through.
I told you, Rich.
You wouldn't even have to flip it. You would have to.
Wait, would it actually just go?
I don't know. It might. It depends, because you have the opening. If you were to dump it in and cork that, it might.
Well, we're not corking it until we dump it in the hot
Right. If you
water.
don't, yeah. It might. Yeah. That's not really a pressure damage.
Well, yeah, because it's gonna get smaller and then it's gonna blow up.
It'll blow up before you can put it. Once it's done.
30 seconds.
Maybe what we'll do is I don't think I'm right. Because I kind of learned what you wrote. But I think what it is has to do with the volume. It goes down to the volume.
I think it's pressure. I mean, I think it's pressure and temperature.
I think it's the volume.
Think about it. How can you heat the can up? It has to be.
So that way the volume
You guys good?
stays, and then
You guys good? Yeah. Evan, you guys good?
give a frozen.
Shelby, you good back there?
Pressure decreased.
Yeah.
Jenny, they including you? Good. All right, put your desk back. Put your desk back.
In the freezer, in the freezer back about 3 days, open up the freezer, there's just frozen Pepsi. There you go.
Okay.
I'm still stuck.
Now, before I explain what happened, we're going to have some people tell us what they think. But before I forget, we got to title these. So there's 3 gas laws. Here they are. This one is called Boyle's Law. Just write it. That's called Boyle's Law. This is called Charles.
Just Charles?
Charles's
Okay.
law. And this is Lusak's law. Or Lussick, some people say. I think it's Lusac. So Boyle's is a pressure-volume relationship. Charles is temperature-volume. And Lusac is temperature-pressure. So those are the 3 gas laws. What that demo, the demo we just did shows really all of them, but mostly these 2. This one doesn't come into play. I mean, it does, but the temperature change is what really doesn't. Okay. So, who would like to share what they came up with in their discussions? Nobody? How about Blake, Jenny, and Shelby? You had three minds back there. Anybody want to?
Okay, so I said how the last thing, like when the volume is constant,
Yep.
how the temperature decreases and then the pressure decreases.
Okay, so you're saying when Devin flipped it into the cold water, the temperature decreased, so the pressure decreased.
Yeah.
In the can?
Yeah.
Okay, and that's why it. What? How would you describe what happened?
I don't know, it like collapsed.
Collapsed. That's how it collapsed. Okay, good. Anybody have something else as to why it collapsed?
Was that right?
Was it? Was it collapsed or crushed?
It was,
So in other words,
it was collapsed because crushed is from the outside.
or
Collapsed is the inside.
did it get crushed from the outside, or did it collapse by getting sucked in from the
It
inside?
was sucked in. Definitely.
Raise your hand if you think it was collapsed from the inside. So it collapsed on itself. Raise your hand if you think it was crushed
I
from
think
the outside.
God
There's only one
smashed
right
it with his
answer.
hands. From the outside.
It was from the inside.
No one thinks it was crushed from the
It was
outside.
crushed.
You think it was crushed?
I think it's crushed too.
You just said it was collapsed.
Oh yeah, maybe it's the low pressure in the
inside.
thing and the high pressure on the outside
Yeah.
crushes it.
Yeah,
That's my
yeah,
final
yeah,
answer.
crushed. Yeah.
That's my final answer, Mr. McCoy.
Anybody else want to share?
I
Xavier?
don't know anymore.
You're making me
Anything
second
different
guess
than
my
what?
life.
You know, some teachers will like give you a hint, like with their body language. He does.
Just listen here, Xavier.
Like they'll be like,
Boiling water flipped upside down to cold water causes the can to compress inside.
Why?
Does pressure increase?
Pressure increased in the can or
pressure left.
out? Wait. Well,
Can I
wait,
come
wait.
in?
Pressure decreased.
Well, it's actually
The pressure increased when I was heating it, right?
Yeah, and then what happened was when you Devin flipped it into ice, it decreased suddenly. So
Decreased suddenly, so it kind of sucked in with the
Can I-
decrease.
Yeah.
Okay,
I have an
that's kind of
idea.
what Jenny was saying.
I have an idea.
Yeah.
Okay, since you brought up this whole crush spectrum, I think what happened was.
Here's my can, by the way.
Okay. So what happened with the can? Can I draw it?
Drop Pepsi some
Okay.
water.
What do you mean? You want to draw what?
The diagram at the top. Alright, so anyways, the heat heats it up and then it's quickly, the pressure in the can goes below what the room is and then it crushes like the flimsy metal.
Okay. So here's the ice. So that's cold. So in here, inside the can, when it's being heated, we have steam. I would let you draw it on another day, but I want to kind of get going here. So is this high pressure or low pressure in here?
It's high pressure right now.
High pressure. Does everyone agree with that? You heat it up, the pressure increases. Why?
Because the heat.
Heat increases. Particles gain kinetic energy. They collide more often with more force. So this is high pressure. Inside the can is high pressure. Yes, we all agree. What about outside the can in this room?
It's like,
Is it lower or higher than in the can?
it's lower.
Lower because it's not as hot. And it's not confined either, right? So we have a small volume and we're heating it up, so there's lots of bouncing and colliding. Is that fair?
Yeah.
But outside, so outside, right, the room, right? Outside in the room here, we have low pressure. Is that fair to say? Compared to inside the can? Yes?
Yeah.
Okay. So then we dump it upside down. All right, and the can kind of does one of these things. Kind of crushes, right? So here's your can. So we put it in the ice. So now inside here, what I'm hearing you guys say is we have low pressure inside the can because of the opposite. We decrease the temp. So what happens to particles when you cool them down? They move slower or faster?
Slower.
Slower. And they're not so far apart. So when we flipped it into the ice, it decreased the temperature inside dramatically. Particles move closer together, so the pressure dropped, right? They're not bouncing around as much. So we all agree with that. What about the room pressure? The room pressure
It's
changed.
higher than the pressure that's in the can now.
Yeah, but did it change?
No.
No, it was the same here. You know what it was? It was actually 1 ATM. We're going to talk about that today. So it was 1 ATM outside. Inside the can, let's say 2 ATM. Now inside the can, let's say 0.5 ATM. Outside, still 1 ATM. So now it's higher pressure outside the room. Guess what the higher pressure does, Ryan?
Crushes it.
It crushes it. So the can was actually crushed by the outside pressure that is now greater than the inside pressure. Because, kind of what you were saying, it drops so fast that there's such a big difference in the pressures just kind of for a second, not even a second. The can can't withstand it because it's not rigid enough. If you did that with a really, 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 really strong container, you know what? Still actually might do it as long as you get that temperature change to be really dramatic. I actually have a demo or a video of this that I want to show you tomorrow. A little different scenario though. Something I'm not willing to do because it's kind of a pain. But
Can you show us right now?
nope. So yes, it was crushed from the outside because you have high pressure and low pressure. So all the gas laws are factoring in here, plus a little bit extra there with the pressure difference and how that would affect something. Okay. So how come things don't get crushed by the air all the time?
Because it's not as quick as that, right?
It's not as dramatic, and pressures are usually equalized, right? So the pressure inside this is about the same as the pressure outside here. It might be a little higher inside here, maybe not this because it's so big, but if you open up a soda bottle, what do you hear? That's releasing pressure. The pressure was greater inside, so if anything, it's pushing out. The air is not pushing in, right? So we reversed that very dramatically, so it was crushed. That's a cool demo. I like it. I think it's a good visual for you guys, so hopefully it makes some sense. All right, still got about 10 minutes now. So we're going to put the gas pressure on hold for a minute and talk about air pressure. What causes air pressure?
Air particles.
Air particles colliding, okay? So we'll come back to those gas laws tomorrow, but right now, real quick, I just want to review this concept with you guys. Don't forget that book work due tomorrow. Let's see, where am I here? Oh, what is STP?
That's the, or do you want to answer it? Or?
No, don't answer it. Do you guys all have reference tables? You need them. Take those out, please. If you need to borrow some, they're right up there. Yes, you have to take them out. I need to show you something.
Does this mean standard temperature and pressure?
Yep.
Ryan, I was writing you on.
Well, yeah, but then I figured out why it crushed. You didn't know why it crushed. You just said it did.
Go to reference table A. That's okay. Who else needs one? Devin? Grab one for Devin, please. Who else needs one? All right. Kayla, what does reference table A say? Standard temperature and pressure. That's what STP stands for. Zach, what are the temperatures on that chart?
101.
I
No,
need
1
temperatures.
ATM.
I need temperatures.
0 degrees
0 degrees what?
Celsius.
What's the other temperature they give you?
Oh, 273 Kelvin.
Good. Those two temperatures are standard temperatures.
It's not absolute zero though.
0 Celsius. when water freezes? 0 Celsius.
Okay.
273 K. 0 K is absolute zero.
Oh,
So
okay.
it's a lot colder than that. It's
Yeah.
273.
Negative 273 degrees.
Water's normal state would be frozen.
Yeah, that makes no sense.
This is standard conditions, not normal conditions. Normal conditions is 25 degrees Celsius.
Okay, so what's standard mean? What's the difference?
0 degrees is standard.
What's the difference?
Right. The temperature. At some point,
No,
somewhere.
like,
And so, hold it.
why
Let me
is-
answer. Somewhere along the line, someone decided standard is 0 degrees Celsius. Normal is 25 degrees Celsius. Why did they pick that? I would say.
okay, so if they asked us a question on a test, what is water at normal STB, we'd have to say frozen, right? Ice.
That would never happen. The test wants you to understand is what that stands for and where to look up the numbers.
Okay.
That's it. Okay. So STP, standard temp, 0 degrees, 273. What about the pressure, Devin? Read those two pressure numbers, please.
101.3 kPa.
Yep.
And 1
1 ATM. Write this down in your notes. You, from now on, are responsible for understanding what STP means. Standard temperature and pressure. Basically, this room has the pressure 1 ATM or 101.3 kPa. That is the air pressure in this room. Go to table D, or chart D. Has all the units on there, or what's it say? Selected units. Find pressure, what does it say? Table D.
PA.
Yeah, what's that called?
Pascal.
Pascal, right. It's called Pascal. We say kilopascals though. We say kilopascals, that's what kPa is. And ATM actually stands for atmosphere. That's the pressure. What pressure numbers do you guys know about in real life? If you want to put pressure in a car tire, any idea what that unit is? PSI, right, pounds per square inch. That's just another unit for pressure. So ATM and kPa are the same thing as PSI, it's just a different unit. Kind of like inches and feet, or centimeters and millimeters. It's all a measure of length, but they're just a little different the way you describe it, right? So there's still units of pressure, barometric pressure, like if you watch the weather forecast, they talk about the pressure, millimeters of mercury, mmHg. It might be changing with a high or a low coming in, different fronts. But anyways, that's a unit of pressure, unit of temperature. That's STP. Okay, I want to explain that because it comes up a lot when we talk about gases. All right, standard temperature and pressure. That's what those numbers are, and that's where you find them. Now, let's talk about air pressure and mountains. Go ahead, draw a little mountain in your notes. Get some snow on that mountain. Okay. Let's say Burns down here. And we are at the base of Everest. Mount Everest, okay? And let's say someone's standing down here. And we'll give them a little funny hat to wear.
It's a really tall person. Who is that? He's really tall. Who is that?
Yeah, he's like 1/5 the size of that mountain.
Yeah.
It's pretty tall.
Blake, that's Blake. Blake's standing there with his
Alright.
little hat and his pitchfork.
Alright.
Now, the top of the mountain.
Who's
Someone
that?
climbed all the way up to the top. We'll make this a girl with super long hair.
Stephanie.
Alright, that's Steph. There we go. Steph can have a hat on too. Okay, we'll get Steph a baseball hat. There we go.
But you're in the mountains, so you're fast.
She's holding a cat.
Made me look like a witch.
Wow.
Michaela, I used
What?
Michaela this morning, and I did draw a witch with a broom for her. Just kind of spontaneously happened. Anyways, so Steph climbed the mountain. She's at the top. Blake's down here farming his land. Check. Now, why am I talking about Blake and Steph in a mountain? Write this down. And you can write it anywhere near the picture. As elevation increases, what happens to air pressure? Don't answer it out loud. And the reason I drew a picture and we're kind of joking around with Blake and Steph here is just so you have more of a visual. And I'm going to draw the air. Okay, I'll draw air particles down here at the bottom of the mountain. I'll draw air particles at the top based on what you guys tell me you think the answer is. This goes for planes too. You ever been in a plane as it takes off sometimes? Who's been in a plane? All right, loud, you good. What happens when it takes off sometimes? Your ears pop, right? Because pressure's changing. That's why that happens. You feel the pressure change. In this room, walking from here to English or lunch or whatever, you shouldn't have a change in pressure. You don't feel it. Your ears won't pop. You don't feel any different. Okay? But when you're changing elevation dramatically, like a big mountain, okay? Not if you drive from here to Albany, yeah, there's a slight change in elevation. It's not really noticeable. Okay? But big mountains, tall mountains, definitely. So, what do you guys think? Raise your hands. As elevation increases, so as we go from Blake up to Steph, what happens? What happens to the air pressure? What do you think?
The air becomes thinner and there's like less particles, so there's less collisions.
So what happens to the air pressure?
It lowers. It goes down.
He says air pressure decreases as we go up the mountain. Who agrees with him?
I agree.
Who's not sure? Who thinks pressure increases?
Exactly, so you're not sure.
Good job. Air pressure decreases. Very good. Air pressure decreases. Very good. But the question is why? So let me draw some pictures here. So down here,
Was it true what I said? Is that why?
Blake has a lot of air to breathe. Why? Because it's very close together. So when Blake is breathing, he gets a lot of oxygen in that breath because it's right in front of his face. It's kind of concentrated. But on top, the air is really spread out. So Steph can't breathe on top of Mount Everest without what?
Oxygen.
Oxygen tank.
That's false.
The only way you could breathe on top of Mount Everest without an oxygen tank, well, in real life it's impossible, but in a fictional environment, you could open your mouth up and run around the mountain with your mouth open and grab all the oxygen as you run around. It's kind of like Pac-Man. Okay? What's Pac-Man do? It's a whole game, but what do they do? Eats those things.
What
Imagine
do
those-
you train yourself
Hold on.
to not?
Those little things, stay with me, are like oxygen molecules. And the only way you could ever breathe is if you could hold your breath long enough to gobble up enough oxygen to be the same amount you get down at the bottom. See, what happens is the oxygen is in front of your face on Blake, it's right here. So I breathe, I don't have to move. But on top of a mountain, the air spreads out. So the same amount of oxygen, but it's just spread out. So it's not right in front of your face. So you can't breathe as well because it's not concentrated enough.
You just gotta run around all day.
You just gotta run around. That wouldn't work. I'm just joking about that. But theoretically, if you could do it fast enough, you could do that.
Didn't someone climb to the top of Mount Everest without an oxygen tank?
Probably.
I don't know. You
I'm
can
pretty sure
train
that's a
yourself to
Exactly.
get better at breathing at higher elevations. A lot of athletes train at higher elevations, like in Denver, let's say. I know there's an Olympic training facility there. They train there because
train
when they
in
come
Denver.
back to normal elevation, their body's like superhuman because it works better. You give it a lot of oxygen, it works better. So if you can perform at a high level where there's no oxygen, come back down where there is some, it's like you have all this
The
energy.
Denver
So-
Broncos are just like,
Hold on, we're not done yet.
Too bad they're awful.
Why
no.
Why does the air thin? You were right. Everything Ryan said was right. There's less collisions on top. We're going to write that. Less collisions, but why? Why does it thin? Why does it expand? Let's write that first. Why? There's less air particle collisions. Less air particle collisions. So the official homework is the book work. Unofficial homework. Answer the question, okay, why? Why are there less? So another why. Why are there less collisions? Why does the air get thin? People say that. The air gets thinner up
Can
and
I
down.
answer it right now?
The question is out there. We'll answer it tomorrow. You can pack up. Don't forget the book
So,
work.
Mr. McCoy, can I answer it
That's
right now?
it.
Just tell it to you. What happens?
Hey, hold on a second.
No, that was